today's video, we're going to talk about geology and earthquakes. Specifically, how does our understanding of the Earth contribute to the models that we use analytically to design building structures? Now, to do that, we're going to go a little bit in depth on tectonic activity, and we're going to talk about some terms related to earthquakes. And then we're going to look at how we make analytical models based off of ground motions and what we do with these models to ultimately determine seismic forces on a building structure. So let's get started. To kick this off, I want to ask the question of what are seismic waves? You may have an idea in your head about a seismic wave and what that might visually look like, maybe a building swaying back and forth, maybe the destruction after an earthquake. But if we really think about a seismic wave, can you imagine what that sounds like? In 1976 in Friuli, Italy, someone was making a recording onto an LP. At that same time, an earthquake struck their building. You can actually hear the seismic waves coming from the earthquake as it struck the building because it moved the needle making the recording. Shortly after that distortion you hear in the recording, you can even hear the building occupants responding to the violent shaking that struck their home shortly after. Now that we've heard an example of seismic waves, we can also provide some textbook definitions. In general, a seismic wave has elastic energy. It's typically low frequency, and the main thing is that the waves propagate through the earth as compared to sound waves, which typically would propagate through the air. Now, there's actually a few different sources of seismic waves, but in general, we're only concerned about seismic waves that come from earthquakes, which really just comes from tectonic activity. Tectonic activity is really important for a few main reasons. One of them is that tectonic activity is going to keep occurring in the future, and the more effort and resources we spend on understanding it and analyzing ground motion records will actually come to fruition if we can better understand the risk that will happen in the future so that we can design buildings to resist earthquake forces. And the second is that when a large earthquake hits, it can have a huge detrimental effect to a society. So it's absolutely worth it to do everything we can to design building structures to resist earthquakes, to maintain our society that we've built. So now we need to ask, what causes an earthquake? What is the source of tectonic activity? To answer that question, we just have to look to the Earth and understand how the Earth was formed. The Earth was made around 4.5 billion years ago, but at that time, it consisted of really hot molten rock debris compared to today, where we have an outer layer that's solid with water over it, and then multiple different layers inside. The main thing here to realize is that through the time of the Earth, the outside has tended to cool off and radiate heat outwards, while the inside has still retained a significant amount of heat from its first creation. That difference in heat creates different layers and is also the driver for plate tectonics. This heat difference creates something called a convection current. It's thought that in the mantle layer, convection currents are carrying heat from the core to the crust, and this heat is actually moving the mantle material itself as well. So this hot mantle material moves up towards the Earth's surface, and when it gets to the Earth's surface, it wants to split and push and move the crust. When you do this to multiple pieces of the Earth's crust, they get split up into something called tectonic plates. The outer shell of the Earth is actually broken up into different sections called tectonic plates. At the interface between tectonic plates is called a fault. Now, this is where earthquakes really occur, is at fault lines. As one tectonic plate is trying to move past another, but it's locked in place because they're solid rock, eventually they build up a lot of strain energy, and once they slip past each other suddenly, that releases the strain energy in the form of seismic waves, which creates the earthquake. Now, at this interface between tectonic plates, or at the fault, there's a few ways we can describe that fault, and this characterizes the type of ground motion that might occur. So one of them is the angle of the fault, which is the dip. So that's how the fault is oriented with respect to the horizontal. And then the other thing is the direction of slip. So how are these two faults going to move past each other? If one of the faults rises up above the other or sinks down, that's called a dip slip. If the faults slide past each other, thinking of a plan view, top-down view, and they slide along the length of the fault, That's called a strike slip. So now we can describe a few different types of faults. There's a normal fault, which is a dip slip fault where the block that's already above moves downwards. There's a reverse thrust fault where it's also a dip slip fault, except the upper block moves upwards after the earthquake. And then you have a lateral strike slip fault. This is where the two blocks slide past each other along the length of the fault. Now, depending on how they slide from the perspective of a viewer facing the fault, it could be a left lateral strike slip or a right lateral strike slip. Now, if there's one fault you want to be familiar with for the seismic exam, it's the San Andreas fault. This fault runs through California. It borders the Pacific plate and the North American plate, and it's a transform fault. So it's a right lateral strike slip fault where they're sliding past each other. Just a few more terminology things. We have the focus and the epicenter. The focus is the actual point in the Earth's crust where the earthquake started, where that fault ruptured. The epicenter is directly above the focus on the surface of the Earth. So you could stand at the epicenter, but you can't really stand at the focus point because it's below the Earth's surface. So now we can talk about something a little bit more interesting, and that is what sort of waves are produced from an earthquake. You heard in that recording earlier that first there was some distortion as the initial waves hit, and then the house really started to shake. And these characteristics of waves can actually describe why at the beginning of an earthquake, the shaking might be different than at the middle of the earthquake or at the end of the earthquake. Now, there's basically two different types of earthquake waves, body waves and surface waves. In terms of timing, body waves are faster than surface waves. Body waves also can move through the interior of the Earth, whereas surface waves only really move at the surface layer of the Earth. Now, the first wave that's experienced in the fastest wave is the P wave, which is a body wave. The P wave travels through compression in the Earth. The second wave that hits is an S wave or a secondary wave. This is also a body wave. Now, the difference here is that the secondary wave or S wave travels through shear in the Earth. This means that S waves can't travel through liquids because liquids don't have any shear resistance. After the body waves come the surface waves. There's a love wave, which is similar to an S wave, except there's no vertical motion, it's all horizontal. And then there's also a Raleigh wave, which tends to move the ground like you would expect to see waves in water. Now, all these waves are a little bit different from each other, but there's one thing to remember in that no matter what, waves all experience attenuation, which is the loss of energy as waves move outward from the focus point. Now, the thing about buildings is that buildings have a fundamental frequency. So if seismic waves hit that building that match up with the fundamental frequency, that's going to excite the structure and it's going to make it oscillate back and forth at its fundamental frequency. When this happens, the building will drift, it could crack the walls, it could damage the lateral system, or it could even collapse. It all just depends on the amplitude of the waves. And you might be thinking, well, during an earthquake, everything is shaking, everything's moving. Why does the fundamental frequency matter versus just shaking the building itself? And this really comes down to the idea of the conservation of energy. When you shake something at its fundamental frequency, it's going to force it to oscillate. And so this is why we really need to be thinking about the fundamental frequency of a building and the idea that seismic waves are like a song and that there's many different frequencies in there and different amplitudes that can affect a building structure. Now, in this video, we can see a physical example of what happens when you shake different structures with different fundamental frequencies on the same base. And what we can see is that no matter what, when the shaking is happening, all of the model structures are moving, but when the frequency happens to match the frequency of the structure, then that structure itself moves even more than the base. And this is where damage happens. So this is what we want to be considerate of and sort of founds the basis of seismic design, is understanding the fundamental frequency of a building structure as it compares to the ground motion. Moving forward, we're going to need to define a few terms when we talk about frequencies of a building structure. So from here on out, we're not going to use the term frequency, which people are probably familiar with. We're going to use the term period. Now, the period is just the inverse of frequency. So frequency is how many oscillations occur per second or per unit time. And the period is the inverse of that. So it's how long does it take for a cyclic motion to get to its starting point. So let's look at this example here. At point A, we can see we have some sort of a frame structure at rest. It hasn't moved. As we go to B, it shifts to the right. Then at C, it shifts back to the center. At D, it moves to the left. And finally, at point E, the frame has moved back to its original point and completed a full cyclic motion. So that time it took to complete the cyclic motion from A to E would be the period of this frame. We could test this out with a frame. Imagine you pull a frame and you let go and it oscillates back and forth. The time it takes to complete one oscillation is its period. So this applies to building structures, single degree of freedoms. Any sort of physical structure can have a fundamental period or a fundamental frequency. I want to introduce the idea of a response spectrum. If you haven't seen this before, it's something that you're going to be using in AAC 7 and you'll definitely use on the seismic exam. But it's basically a plot of period versus spectral acceleration, velocity, or displacement. This answers the question of how do I know what the maximum acceleration is going to be from a ground motion for a building of a specific period. So what we could do to use this is if we know our building period, we can enter this plot and then determine the acceleration, which is incredibly valuable. That's the whole issue here, is that depending on the period of a structure, it can experience different accelerations. Now, before we just start using this, I think we need to go a little bit further and to understand exactly how do we make a response spectrum. To create a response spectrum, typically you'll take a single degree of freedom structure and then subject it to ground motions, perform some mathematical analysis, and then you can make the plot. So what is a single degree of freedom structure? It's honestly just the most simple way you could model a building or something physical that's similar to a building structure. And it actually works out quite well. So you could think of like a lollipop, something that has a long stick with a mass at the end. How could you move that physical system? Well, you have one mass at the tip of there, and so that mass can move around in one plane. So it can move to the left, it can move to the right, but that's still just one degree of freedom. And the benefit of doing mathematics for an SDOF is the fact that it's relatively easy to do the math on it. As soon as you add another degree of freedom, things have become much more complex because you have actually multiple ways that that system can move. For an SDOF, because there's only one degree of freedom, you can calculate the period for it, and that is the only period. That is the only way it can move. Every time you add another degree of freedom, you actually have another way the structure can move, and so now there are multiple periods, and your analysis becomes a lot more complex and honestly unnecessary. So now we can do a really high-level overview of how we make a response spectrum. So essentially, we take an SDOF at a specific period, and we analyze that SDOF assuming it was experiencing a record ground motion. This requires solving a lot of really complex equations, and you have to solve it in specific time steps, but then you would develop 3 new plots: the displacement plot, velocity plot, and acceleration plot. So for this SDOF, for that ground motion, here's how much it moved through time, here was its velocity through time, and here was its acceleration through time. So then you can just take the maximum acceleration experienced through the entire ground motion record and plot it. And so now you have one plot on a response spectrum. If you repeat this process, now do the same process again with an SDOF at a different period, you could put a new point on your plot. You keep repeating this for different periods, and eventually you can create a full plot. Now with that full response spectrum, you could potentially use it for an analysis, for a building structure, or whatever else you're doing. Now let's do an actual example of using a response spectrum. Remember, all we have to do to use it is, given a period, we enter in the graph, we read off the corresponding number for the spectral acceleration. So let's assume we had a building that weighs 100,000 pounds, or 100 kips, with a fundamental period of 0.4 seconds. We would enter our response spectrum at 0.4 seconds and read off the value of 0.7 for our spectral acceleration. Now with our spectral acceleration, all we have to do is multiply that acceleration by the weight of the building to get our design lateral force. So it's F equals ma, Newton's second law, 0.7 times 100 kips is 70 kips. and that would be our answer. So if you got this exact question on the exam, there would be nothing else for you to do. If there was more information provided that talked about occupancy category, building type, the lateral system, then we would actually have to use AC7 to develop a more sophisticated answer, which you'll see in later videos and in Chapter 12 of AC7. But for this example, this is in general how you use a response spectrum. There's one last thing I want to note about this equation, in case it confused anyone. I did reference F equals ma, where m is a mass, but as I wrote it, I wrote 100 kips for the mass. Kips is a force, not a mass. It's sort of implicit that you would have to divide kips by Earth's gravity constant to turn it into a mass, at which point the g's would cancel and you'd be left with 70 kips. That isn't really going to be an issue when you're reading AC7 because AC7 doesn't denote it F equals ma, they denote it V equals C sub S times W, and they explicitly state W is the weight of the building, which would be in pounds or kips. And C sub S is just a unitless factor to reduce it and turn it into the base shear. So hopefully you're not confused by that, but just remember if you see this written out like that in the future where you have kips multiplied by a constant multiplied by G, that kips is sort of implicitly divided by Earth's gravity. So that's about it for the technical stuff that we're going to cover related to earthquakes, geology, and response spectrum. The last thing I want to discuss in this video is going over a brief timeline of some advancements in how earthquakes have been quantified, especially in the past few hundred years. Our understanding of plate tectonics has really only been about 50 years old, but way before then, people were still experiencing earthquakes. So without any scientific way to explain them, they would often refer to the sources as being mythological creatures like Namatsu in Japan, which was a giant catfish that would break free of its handlers and create tsunamis and earthquakes, or even Poseidon. Now, if we go back to when people were trying to do more analytical ways of looking at earthquakes, we might be able to start at 132 CE when we have this dragon jar, which would release a ball during a ground motion, and this was not so much an analytical record, but it really sets the stage for people thinking about and trying to do something to record earthquakes. Fast forward to 1855, and we get a mercury-based seismograph. Now, this was interesting because it was the first one that could actually tell what time the earthquake hit. There was an electrical signal that would get sent to a clock to force it to stop once enough shaking had occurred, and this one also would record the duration, intensity of a seismic ground motion. In 1880, we get the first modern-looking seismograph. This one, of course, has a suspended mass, but also, interestingly enough, it has photosensitive paper and a light source, and that was its means for recording the intensity and duration of the seismic event. In 1883, we get a 10-point intensity scale. Now, intensity scales are qualitative. They rely on people giving verbal descriptions of what they saw or what they felt to describe the impacts or effects of an earthquake. These can still be used, though, to map out where an earthquake started, because if you were to talk to enough people, you could probably, through mapping out the responses and the intensity scale, determine where was the largest intensity, and therefore, where was the source of the earthquake. In 1902, Mercalli provides another intensity scale. This one, again, it's 10 points. It's based off of some modifications to the Rossi-Forel scale. Later on, he would eventually add 2 more scales to this to make it a 12-point scale. In 1906, the San Francisco earthquake hits. Now we see an intensity map here, but we also see some ground motion records from seismographs. So in the early 20th century, there was both intensity scales and seismograph recordings. In 1931, Wood and Newman would take Mercalli's scale, modify it slightly, and come up with the modified Mercalli intensity scale, which is something that's still used today as a point of reference. In 1932, the U.S. government funds the creation and deployment of strong motion seismographs. Now, the significance of this is it marked a thinking point, thinking about how are we going to build better buildings that can resist earthquakes. The first step is recognizing that if we can record ground motions, maybe then we can better understand ground motions and better design building structures to resist them. So because of this funding, from 1932 onwards, a lot of significant earthquakes were recorded by really well-made seismographs, and we have records of this that we can still use today in seismic evaluations. In 1935, we got a quantitative scale that's still referenced today, and that is the Richter magnitude. So this is a quantitative scale, meaning it's taken off of a measurement that you would quantify somehow, specifically a Wood-Anderson seismograph, the maximum amplitude recorded from that seismograph, plug into this equation, and you get the Richter magnitude. This is logarithmic as well, so a magnitude 8 earthquake would have 10 times as much wave amplitude as a magnitude 7 earthquake. In 1941, George Hausner at Caltech starts publishing calculations for analyzing ground motions. Specifically, he started looking at taking ground motions and figuring out a velocity spectrum for them. Now, this is really important because this is sort of the start of analyzing ground motions to turn them into a response spectrum, which, as you've seen, is the basis of how we determine our forces on building structures today. In 1979, we get the moment magnitude scale. This is the current magnitude scale that you would use if you were referencing earthquakes today. The benefit of using this scale versus the Richter magnitude scale is the Richter magnitude scale relies on a physical seismograph doing a recording. Now, that seismograph has its own period and has its own sampling rate. So at really high magnitudes, the Richter magnitude scale can't really differentiate between 8, 9, 9.5 earthquakes as clean and accurately as the moment magnitude scale. The moment magnitude scale relies on the seismic moment, which really looks at the actual fracture or movement of the earth from the earthquake. What's the rigidity of the rock? What was the area that ruptured? What was the distance that the fault moved? This is a different type of science, and you can see how it might be a little bit more accurate than relying on a seismograph. So this is the preferred way of describing earthquakes today. And finally, in 1982, Newmark and Hall published a paper on developing response spectrums from ground motions. And this is basically the culmination of everything that's come before, including the seismographs and the work by Hausner. And this result, the output, this response spectrum, is what you'll see in AAC7. And that's it for this video. If you have any comments or questions, please feel free to leave them below the video. Otherwise, good luck on your studies.